Imagine you're looking for a friend in a small, cozy room with just four people. You'd find them in seconds, right? Easy. But what if the room turns into a massive, packed stadium with 10,000 people? Suddenly you're running, you're searching, and you're sweating. The problem stayed the same, that is to find the friend, but the effort exploded. Hi everyone, welcome to Algo Snack. Today we are building one of the most important foundations in all of computer science. We are going to master the language of efficiency so you can stop guessing and start knowing exactly how your code scales. Here's our roadmap. We'll define time complexity and meet our main variable n. We'll dive into the big O family, including big O, omega, and theta. Finally, we'll see why worst case is the one everyone asks about in the interviews. So let's dive in. When we work with very small inputs, many algorithms seem fast enough. If you test a program on just 10 elements, almost everything may appear efficient. But when the input grows to thousands or millions of elements, the difference between algorithms becomes huge. A solution that felt fine for small data may suddenly become too slow or even unusable. This is why today's engineers don't just care about how fast an algorithm is right now, they care about how its running time grows as the problem becomes larger. This idea of studying how the amount of work grows with the size of the input is called time complexity. It is important to understand that time complexity does not refer to seconds on a clock. Instead, it refers to the number of steps or operations an algorithm performs as the input of the size increases. To talk about input size clearly, we use a simple variable n. If an array has 5 elements, then n is 5. If an array has 100 elements, then n is 100. So, n is simply a way to represent how big the computation problem is. Let's take a simple example. Suppose we want to search for a value in an array by checking each element one by one. If the array has 5 elements, we may need up to 5 checks. But if the array has 10 elements, we may need up to 10 checks. So when the input size doubles, the amount of work also doubles. This type of predictable growth is called linear growth. In algorithm analysis, we describe this using the notation O of n. You may wonder why notation exists. As problems become larger, different algorithms grow at different speeds. Some algorithms increase their work slowly as input grows. Others increase very rapidly. To compare algorithms meaningfully, we need a standard language to describe these growth patterns. This is where asymptotic notations like big O come into the picture. Let's look at big O through the lens of your morning commute. Think of big O as your absolute worst case scenario. Imagine every traffic light is red. Big O tells you, even on the worst traffic day imaginable, it will take you at most 60 minutes to get to work. Your commute might be faster, but it will never be slower than this bound. It is the ceiling. In programming, we use this to describe the maximum growth of an algorithm. Take a linear search, for example. If the item you're looking for is at the very end of a list of a million items, you have to check every single one. That maximum effort is what we call big O of n. Now, what about the opposite? That's big omega. This is your best case scenario. Imagine it's 3 a.m., every single light is green, and the roads are empty. Big omega tells you the absolute minimum time required. It says, even if the stars align, you physically cannot get to work in less than 15 minutes. It's the flow. You'll never be faster than this limit. For our algorithm, Big Omega describes the minimum work. If you find your target in the very first box you check, the work is constant. no matter how big the rest of the list is. We represent this flow as big omega of 1. Happens most of the time. That's where big theta comes in. If your commute consistently takes between 30 and 40 minutes every single day, regardless of a few extra cars, we say you have a tight bound. Big theta means the ceiling and the floor are essentially the same. For an algorithm, it tells us this is the exact predictable growth you can expect every time you run this code. It's the sweet spot of algorithm analysis. In linear search, if the value is found immediately, that is the best case. If we must check every element before finding it, that is the worst case. Finding your friend at the very first door is the best case. Checking every single person in the stadium, that's the worst case. Most of the time, you are somewhere in the middle, the average case. It is important to understand that asymptotic notations are not the same as best case, worst case, or average case. Notation tells us how growth is described. Cases tells us which situation are we analyzing. The same algorithm can have different behavior depending on the input. In coding interviews, we often focus on worst case behavior because real systems must remain reliable even under heavy or unfavorable inputs. So, everything we discussed today comes back to one simple question. As the input size grows, how does the amount of work grow? Time complexity helps us answer that question using notations like big O, big omega, and big theta. Here is a question for you. If the input size doubles and the amount of work becomes 4 times, what kind of growth pattern could this represent? Write your answer in the comments. In the next video, we'll learn how to simplify time complexity expressions, identify dominant growth patterns, and explore ideas like amortized analysis.